Hello. I want to continue the analogy in rotational motion and comparing it with linear motion. And now I want to take a look at work. Fortunately, work is work in the sense that it's going to have units of joules. In linear motion, you have work is equal to the magnitude of the force times the magnitude of the change in displacement times the cosine of the angle between them. If we look at the angular variables, instead of force, we have torque. Instead of change in displacement, we have change in angular displacement. And then we have a final factor that I call cosine phi. This is a very general term, but in this class, we are only going to look at two different situations. So really what you're going to need is work in rotational motion is equal to torque times change in angular displacement. And then you need to check one other thing. Is this torque trying to speed it up? Then cosine phi equals +1. Is this torque trying to slow it down? Cosine phi equals -1. That's pretty much the same as work in linear motion. If you do positive work on an object, you're trying to speed it up. If you're doing negative work on an object, you're trying to slow it down. This is the same idea here, except speeding up means it spins faster and faster, and slowing down means it spins slower and slower. So as far as this course is concerned, in angular motion, work is equal to the magnitude of the torque times the magnitude of the change in angular displacement measured in radians, and then it's either positive or negative depending on whether it's trying to speed it up or slow it down. Let's take a look at an example. We have a solid disk with a mass of 12.2 kilograms, and it is initially spinning with an angular velocity of positive 173 radians per second. The positive means it's spinning counterclockwise. Now we have two forces acting on it, and each of those forces is creating a torque. One of the forces is 29.4 newtons. It is 0.212 meters away, in fact, to the west of the center of the disk, and is pointing straight down. And the other is 52.5 newtons. It is pointing straight up. It is on the rim, acting on the rim of the disk, which is 0.311 meters away from the center. And the location where it's acting is exactly southeast of the center. So you can see the diagram down here with the locations of those two forces. The calculation of the net torque, first ask yourself what these torques are trying to do, these individual torques. The disk is spinning counterclockwise. We know this because of the positive angular velocity. The torque on the left, is it trying to increase the rate at which this disk is spinning, or is it trying to slow it down? And if you visualize this, you should see that the force on the left is creating a torque that has a counterclockwise orientation, so it is trying to speed it up. As it turns out, the force on the right also has a counterclockwise orientation, and so it is also trying to speed up the rotation. Therefore, both of these torques are going to do positive work. But we need to figure out exactly what that number is. And our first step is to figure out what this net torque is. They're both acting in the same direction. They're both acting counterclockwise, so I will add them up. Each one can be determined as r, the distance from the axis of rotation to where the force is acting, times s, the magnitude of the force, times the sine of theta, where theta is the angle between r and f. For force 1 on the left, the angle is 90 degrees, but for force 2 on the right, the angle is 45 degrees. We plug in the other numbers for r and f as given in the problem, and we get that the magnitude of the net torque is 17.8 newtons times meters. Now that we know the net torque, we can start finding some other quantities. Keep in mind, this is a 12.2 kilogram solid disk. That tells us information that allows us to calculate the moment of inertia. Since it is a solid disk, K is equal to 1/2. Our expression for the moment of inertia is capital I equals 1/2 mr squared. And we plug in the numbers that we have, and the moment of inertia is 0.590 kilograms times meters squared. We now have the net torque. We have the moment of inertia. By Newton's second law, that allows us to find the angular acceleration. Angular acceleration equals net torque divided by moment of inertia. So 17.8 from the previous slide divided by 0.590 from this slide, we get that the angular acceleration is 30.1 radians per second squared. And then we need to calculate the angular displacement. Remember that the change in the angular displacement is indispensable in calculating the work done by a torque. So, how do we get the angular displacement? Well, we do a little angular kinematics. Theta final equals theta initial plus omega initial times t plus 1/2 alpha t squared. The time given in the problem is 10.3 seconds. And the initial angular velocity is 173.3 radians per second. And we just calculated the angular acceleration, alpha, to be 30.1 radians per second squared. Plug in all the numbers. And if we assume theta initial is 0, which is our rule of thumb, we get theta final equals 3,383 radians. So the change in the angular displacement, delta theta, is 3,383 radians, which finally allows us to calculate the work done by each individual force. The work done is equal to the torque times the change in angular displacement, and then times either +1 or -1. In this case, we multiply by +1 because these torques are trying to speed the object up. We plug in our numbers, and we get that the work done by the first force is 21,090 joules. And through a similar formula, the work done by the second force is 39,060 joules. Of course, we can add these up. We would get about 60,000 joules for the total work done on this disk. Let's move on. The work energy theorem requires a little bit of revision. I'm not adding any new potential energies to this equation, but I'm now taking the total kinetic energy and I'm breaking it up into a linear or translational portion and a rotational portion. So with that specific distinction made, our revised work energy theorem can be written as the work done by non-conservative forces equals the change in the translational kinetic energy plus the change in the rotational kinetic energy plus the change in gravitational potential energy plus the change in elastic potential energy. Let's take a look at an example. We have a solid sphere with a radius of 12.2 centimeters. It rolls down a length of 2.50 meters that is inclined at an angle of 25 degrees. The sphere rolls without slipping. That's actually kind of important, and I'll explain why as we go through the solution. And the question is, if it is released from rest, how fast is it moving at the bottom? We're not worrying about friction here because one of the reasons why is because it says without slipping. So that tells us we don't need to worry about friction sliding this across the surface. There is a normal force that's present, but the normal force is perpendicular to the direction of motion. So the non-conservative forces, one of them is not causing any motion, and the other is perpendicular to the direction of motion. So the work done by non-conservative forces is 0. On the right-hand side, we have that the center of mass of this sphere is moving, so we are going to get a change in linear kinetic energy. We also have that the sphere is rotating as it rolls down the incline, so there's rotational kinetic energy. We get a change in height, so there's a gravitational potential energy component, but there is no spring, so we don't worry about elastic potential energy. The change in height of the sphere is 2.5 times the sine of 25 degrees. You can imagine a right triangle. The hypotenuse is 2.50 meters. The angle of 25 degrees is with the adjacent. The opposite side is the vertical side, and we use sine to find that in this circumstance. Now, let's start looking at the work energy theorem. We know that the work done by non-conservative forces is zero. That's going to be equal to the change in regular kinetic energy plus the change in rotational kinetic energy plus the change in gravitational potential energy. Like I said, we don't have elastic potential energy. But furthermore, it says the sphere is initially at rest. So V initial is zero and omega initial is zero. And then it arrives at the bottom, so H final is zero. So of the 6 terms on the right-hand side, 3 of them are zero. And we are left with 1/2 mv final squared plus 1/2 times the moment of inertia times omega final squared minus mgh initial. Now the moment of inertia goes as kmr squared. And in the next equality, we take the r squared and the omega final squared and we lump them together. In parentheses, we get r times omega final quantity squared as a factor in the middle term. Didn't change the first term, didn't change the last term, and I just rewrote the middle term. And the reason I did that is I want to take further advantage of the fact that this is rolling without slipping. If it is rolling without slipping, then the tangential velocity of the outermost point on the sphere has to have the same speed as the center of mass of the sphere. In other words, r omega final, where r is the radius of the sphere, has to be equal to v final. So if we make that replacement, we get 1/2 mv final squared plus 1/2 kn v final squared minus mgh initial. We can play around with the algebra a little bit to solve for v final squared. We get v final squared is equal to 2 times gh initial divided by 1 plus k. I kept this as general as possible. This is true for any rolling object. It would also be true for an object that was sliding down frictionlessly. If there's no rotation whatsoever, then k is 0. But if we have a rolling object, if it's a rolling sphere, a solid sphere, a hollow sphere, a rolling cylinder, a solid cylinder, or a hollow cylinder, you have the formula. All you need to do is plug in the proper value of k. In our problem, the shape is a solid sphere, and so k is equal to 0.4. So 1 plus 0.4 is 1.4. We have gravity is 9.8. We have h initial, which we calculated near the top as 1.057. V final squared equals 14.8. V final equals 3.85 meters per second. A quick recollection for you, I hope. We have 2 objects rolling down a ramp. They both start from rest. One of them is a solid disk. The other is a hollow disk. They have the same mass. They have the same radius. Which reaches the bottom first? The disk, the ring, they both reach it at the same time, or some sort of strange option number 4 where an extra dimensional force comes into play and completely messes up the physics of our universe. Let's hope it's not option number 4. Let me know if you have questions at the start of class. Angular momentum is the angular counterpart to regular old momentum. We looked at regular momentum very recently. We said that little p equals mv. Little p is a vector, and v, the velocity, is a vector. Little p is the momentum. Of course, we have an angular counterpart, otherwise I wouldn't be bringing this up. The angular counterpart to momentum is unoriginally named angular momentum. It is represented by a capital L. The calculation of angular momentum looks like mv except with the angular counterparts. Instead of m, the mass, we have moment of inertia, capital I, and instead of v, the velocity, we have lowercase omega, the angular velocity. I can always calculate L equals I omega. On the other hand, if I have a small particle, maybe like a point particle, that is moving, it might be more convenient to calculate the angular momentum as r times p times the sine of theta, where r is the distance from the center of rotation to where the object is, this point-like object is, p is the momentum of that object, and then theta is the angle between r and the momentum. Let's look at an example. Now let's understand this a little bit and then we'll look at an example. On the screen, you see a picture of a small black circle labeled M. That's just a moving point particle of mass M. And you can see a black arrow labeled lowercase v. That represents the velocity of this particle. The length of the arrow indicative of the speed, and of course the direction of the arrow, the direction of motion. There are also two x's on here. If you are standing at the x to the left, then the moving mass has a clockwise motion relative to you. And if we wanted to calculate the angular momentum using rp sine theta, we'd have to stick a negative sign in front to take into account that clockwise motion. But perhaps strangely, if you're standing at the x on the right and the ball is moving, it's in the exact same location as it is now, moving with the velocity that you see. If you're standing at the x to the right, then in that circumstance, the ball actually has a counterclockwise orientation to its motion. And you would say that the angular momentum, therefore, is a positive quantity. So this is a little bit weird. One person can say the angular momentum is negative. The other person can say the angular momentum is positive. As long as it can be justified, it's okay. It's not going to wreck the universe or anything like that. Here's the example. And it's October. We got to talk baseball. The situation in this problem is that the outfielder sees a ball high overhead sailing out of the park. The ball is 3.5 meters above the outfielder at a given instant. It has a speed of 28.1 meters per second, and it is moving in a direction that is 18 degrees below the horizon. We'll assume that the ball, like a standard baseball, has a mass of 145 grams. And the question is, what is the angular momentum of this baseball? This has to be solved using the point particle formula for angular momentum. A baseball is passing far over the head of an outfielder, can be approximated as a point particle. We're going to treat it that way. The momentum has a magnitude of m times v. M is 0.145 kilograms. V is 28.1 meters per second. The magnitude of the ball's momentum is 4.0745 kilograms times meters per second. The angle between the momentum of the ball, which is represented by the black arrow, and a line from the outfielder's head to the ball. We're going to treat the outfielder as the center. Things are from the perspective of the outfielder. The line, when it's directly overhead, is straight up. The angle between this radial line, this straight up radial line, and the direction of the velocity, the angle from straight up to horizontal is 90 degrees, and the angle from horizontal to this velocity is another 18 degrees. So the angle is 108 degrees. The angle theta is 108 degrees, r is 3.5 meters, and the momentum P has a magnitude of 4.0745 kilograms times meters per second. So I can find the magnitude of the angular momentum, and I get that the magnitude is 13.5 kilograms times meters per second squared. Now, this ball has a clockwise component to it. So the magnitude of the angular momentum is 13.5 kilograms times meters squared per second. But if I had to write down the angular momentum, I would have to say that the angular momentum is negative 13.5 kilograms times meters per second squared. I have to introduce that minus sign because of the relative location and motion of the ball compared to the center of my system. If my outfielder was in some other location, it might be positive. But in this case, in this orientation, if I wanted to express the angular momentum, I would need that minus sign. A little bit crazy. Let's get back to this. We want the angular velocity. Well, I'm going to need the moment of inertia. I'm treating the ball as a point particle. If it's a point particle, then K is 1, and the moment of inertia is capital I equals mr squared. N is 0.145 kilograms. R is 3.5 meters. I square that. I get that the moment of inertia of this ball is 1.77625 kilograms times meters squared. And now I can solve for the angular velocity. The magnitude of the angular velocity is equal to the magnitude of the angular momentum divided by the moment of inertia, I. So 13.5 divided by 1.77625 equals 7.64 radians per second. But as I said before, this has a clockwise orientation. We got to plant a minus sign in front of this, and our angular velocity is negative 7.64 radians per second. Moving on. There's a law of conservation of momentum. There's a law of conservation of angular momentum. We can see a couple of videos on this. For instance, this person right here sitting in a chair, he is extending these hammers out to one side or the other. He's not changing really his own moment of inertia, but each hammer has a moment of inertia. And if we treat the hammers as point particles, then the farther they are from the axis of rotation, then the greater the moment of inertia they have. So let's take a look at what happens when he starts spinning and he brings the hammers in. His moment of inertia decreases when he brings the hammers in, and his motion speeds up. He brings the hammers back out, his moment of inertia increases, and he slows down. This is an example of conservation of angular momentum. At all times, the total moment of inertia times the angular velocity is equal to a constant. But if the moment of inertia increases, the angular velocity has to decrease. Now imagine another situation where we're going to use conservation of angular momentum. We have a playground merry-go-round, diameter of 5.7 meters and a mass of 73.2 kilograms. We're going to treat this merry-go-round as a solid disk. Perhaps the merry-go-round is just been vacated by another child who leaves it rotating with an angular speed of 7 RPM, 7 revolutions per minute. But then another child decides, I'm going to run up to this merry-go-round, and I'm going to jump onto it. I'm going to jump onto it at the edge. Crazy child. The second child, let's say, will have a speed of 3.1 meters per second at the instant they make contact with the merry-go-round. They're moving tangentially to the merry-go-round rather than directly towards the center. Let's say their mass is 47.1 kilograms. How is the angular velocity of the merry-go-round going to change? What is that final angular velocity going to be? As I said, we're treating the merry-go-round as a solid disk, so its moment of inertia is 1/2 mr squared. Plug in the mass of the merry-go-round. The diameter of the merry-go-round is given. Pay attention to that. The diameter is given as 5.7 meters. The radius is half the diameter. So we do 5.7 divided by 2, and we square that result. And I calculate the moment of inertia of the merry-go-round to be 297 kilograms times meters squared. The child is going to be treated as a point mass, the second child who runs and jumps onto the rotating merry-go-round. We'll treat them as a point particle. At the instant they make contact with the edge of the merry-go-round, they are 5.7 divided by 2 meters away from the axis of rotation. So their value of r would also be 5.7 divided by 2. Their mass is 47.1. We're treating them as a point mass, so k is 1. And so I calculate the moment of inertia of this second child to be 383 kilograms times meters squared. If they chose to land on a different location on the merry-go-round, that would change the value of their moment of inertia, but we have them on the edge of the merry-go-round. So 383 kilograms times meters squared. The total angular momentum of the system after the child has jumped on angular momentum, the total moment of inertia of the system after the child has made contact with the little merry-go-round is the sum of the two separate moments of inertia. So that 297 plus 383 is 680 kilograms times meters squared. Now, I'll tell you this. This is in rotation exactly what a perfectly inelastic collision is like in linear motion, because the child and the merry-go-round will have the same final angular velocity because they're stuck together. But the initial angular velocity of the child is dependent upon their tangential velocity at the instant just prior to making contact with the merry-go-round. They're running with a speed of 3.1 meters per second. They are running tangentially and towards the edge of the merry-go-round, so the radius at which they land on the merry-go-round is 5.7 meters divided by 2. So I have to take the 3.1 meters per second for their tangential velocity. I have to divide by the radius of the little merry-go-round, and I get that the child's initial angular velocity is 1.09 radians per second. The initial angular velocity of the merry-go-round was given in revolutions per minute, and that's not standard. We have to convert revolutions to radians, and there are 2 pi radians per revolution. And we have to convert minutes to seconds, and there is 1/60th of a minute per second. With these factors, we get that the initial angular velocity of the merry-go-round is 0.733 radians per second. Now we can apply conservation of angular momentum. The moment of inertia of the child times the initial angular velocity of the child plus the moment of inertia of the merry-go-round times the initial angular velocity of the merry-go-round. That's a typo. That should be omega 1 initial. And that's equal to the moment of inertia of the child plus the merry-go-round. So 383 times 1.09 plus 297 times 0.733 is equal to 680 times omega final. 383 times 1.09 plus 297 times 0.733 is equal to 635. So omega final equals 635 divided by 680. That's 0.934 radians per second, and we can show that's equal to 8.9 revolutions per minute. I want to point out that there is an impulse momentum theorem. Well, there's a variation for rotational motion, but keep in mind the impulse momentum theorem is just Newton's second law, F equals ma. Well, now we have torque equals I alpha for Newton's second law in rotational motion. And just as you can show that the impulse momentum theorem, net force times time equals change in momentum, just as you can show that from Newton's second law, you can also show that net torque times time equals change in angular momentum. Might be good practice for you to do this. Go back a few lectures, look at the derivation of the impulse momentum theorem of Newton's second law, and see if you can follow the steps and duplicate them for the impulse momentum theorem for angular motion. Not requiring it, but if you want a suggestion for studying, I don't think that's a bad one. I want to recap the analogies that we have between linear or regular motion and angular motion. We have analogies for displacement, velocity, and acceleration. We saw those in circular motion. But in this chapter, we added an angular counterpart to mass, to force, to momentum, and in our calculation of kinetic energy, and in our calculation of work and what have you. But we have a bunch of analogies with all of these concepts. Make sure that you understand which is which, and the equations that we have for the linear or regular motion, they behave exactly the same way in angular motion. So don't lose sight of the forest because of all the trees. There's a lot of stuff on this slide, but there are so many parallels. It's almost like if you can learn it for one set, then you've learned it for the other set. We also find the tangential variables that kind of relate the angular variables to linear variables. So we have tangential displacement, which is r times theta, tangential velocity, which is r times omega, tangential acceleration, which is r times alpha. And we can kind of extend that to moment of inertia and torque and angular momentum, which all have factors of r in them. And we also have rotational kinetic energy, just for the sake of fun. Finally, I want to revisit Kepler's third law of planetary motion. Remember Kepler's laws that the planets orbit the sun in elliptical orbits, and that they square the period is proportional to the cube of the distance. Well, this one here sweeps out equal areas and equal times, and this is actually conservation of angular momentum. There is a force that attracts the planet to the sun, a gravitational force that acts over some distance r. The angle between the two is 0. So what that means is if there is angular momentum, the torque that the sun exerts on the Earth is 0. So if the Earth is placed with angular momentum, and if the torque exerted by the sun on it is 0, then the angular momentum is not going to change. That's an example of the impulse momentum theorem for angular motion. Torque times time equals change in angular momentum. Well, the torque is 0, so I don't care what the time is. It results in the change in the angular momentum being 0. So whatever initial angular momentum there is, that's going to stay constant. But as we see, when the planet is further from the sun, it slows down. When the planet is closer to the sun, it speeds up. So we can imagine triangles representing the areas swept out by the planet. And when it's far from the sun, the base of the triangle is relatively short. And when it's near to the sun, the base of the triangle is relatively long. Now I'm talking about for the same periods of time. It's moving slowly so it doesn't move as far in, say, a week as it does when it's closer to the sun. It moves a slightly greater distance over a week. The area of the triangle is 1/2 base times the height, but the base is the distance it travels. The base would be equal to speed times time. But if we treat the planet as a point mass, then the angular momentum is equal to r times p, rmv. R is equal to V is equal to L over mr. And V delta t, the length of the base of the triangle, can be written as L times delta t over mr. That's the base of the triangle. The height of the triangle is the distance from the planet. It's basically r. And so what we get is a cancellation. We have an r in the denominator, and we have an r representing the height. They cancel out. We get that the area of the triangle is 1/2 times L times delta t over m. And this constant, that's the mass of the planet. L is constant because the torque on the planet is 0. And if we keep the same delta t when it's far from the sun, if we say delta t is 7 days, if it's near to the sun, we say delta t is 7 days, then delta t is the same. And the area swept out by the triangle is the same. So way back when I introduced Kepler's laws of motion, I said that this one was from conservation of angular momentum. That's what we have here. My goodness, that's enough. Bye-bye.